In this lecture, we are going to learn about page replacement algorithm. So what are page replacement algorithm? We saw last time about demand paging. Okay, so what happens in, we saw that in when you have virtual memory management, then you don't bring all the pages for a particular process into the main memory. So if this is your main memory, your process P1 requires 100 pages. Usually it will just execute, and for execution it will require around 25 pages. So you bring those 25 pages here, okay, and execute P1. But now let's say somehow it is executing some pages, let's say from 70 to 80, which are not there in this main memory. So what will you do? In that case, what happens is we need to go back to the secondary memory, okay, and bring back those pages into the main memory and execute them. This is the page replacement you need to do. So when we see that in the main memory, but let's say other processes, all the pages are occupied. In the main memory, everything is occupied, so with different pages for different processes, let's say P1, P2 and P3. So now the thing is, what should I replace? So I have to bring pages from 70 to 18 for process P1. So, and there is no place here. So what I need to do, I need to do a swap. So I will put some pages that are not being utilized in the main memory back to the secondary device storage, and then bring those which are required to the main memory. So that's the thing. The page may be brought into main memory several times. So we have page, this is known as page replacement. So we are replacing pages that are needed by pages that were not needed. So page replacement prevent over allocation of memory by modifying page fault service routine to include page replacement. So one thing is, of course, so if let's say your program requires 100 pages, you give it 100 pages in the main memory, there will never be a page fault. You will never require page replacement. But the thing is, you will be doing over allocation and you will be using too much of your main memory, which is a precious thing, okay, which is quite costly. So what happens is, we say that okay, we will use only those pages which are usually executed, we bring them. But if you need some different page, okay, or something which you require, then we can always go back to the secondary memory, bring those pages into the main memory. So use modify bit to reduce overhead of page transfer. So only modified pages are written to the disk. Okay, again, so if we bring some page into the main memory, so there is a modify bit or a dirty bit which says that okay, so when we are swapping, let's say I was using this page, now with page replacement policy, somehow I'm not needing this page, I swap some new page with this one. So I will copy this one only when if it was modified. If it was not modified, I will leave it. This saves your input output. Okay, page replacement completes separation between logical memory and physical memory. So we can, this is what I can over allocate based on virtual memory. So I have 4 processes running, okay, and then what happens, I have 4 processes running, each one of them may require 200 pages. Let's say I have only 100 page in my main memory. So what will I do? I will just use 25 pages for each one of the processes, and if they require other pages, I will use some page replacement algorithm to bring them. So need for page replacement. So I have 2 processes, each one of them have 4 lines of instructions, or in fact 4 pages. And then what they do, so page table, here is page table for user 1, here is page table for user 2. So for user 1, 3, 4 and 5, okay, so this is frame, okay, so let's see what it is. So this is page 0, 1, 2, okay, so this is D. Let's see about 2, 3. In 3 you have what happens here. So this is the main physical memory. Okay, so you have A, B, D, E here, and this is the page table. It says in 6 I have A, here you have A, so which is the frame number 6. You have page number 0, and then you have page number 2. Okay, so this one you have D here, so page number 2 is in frame number 2. Page number 3, okay, is in frame number 7 here. Okay, so this is the page table. It says these are valid, but B is, which is page number 1, is not there here. Okay, so it is invalid. I have not brought it into the main memory. It is there in the hard disk. Similarly, if you see here for process P1, H is here, so it is in frame number 3. So page 0 is in frame number 3. Page number 2, J, is in frame number 5 and 4. So 1 is valid, so it is load M. Here it is in page number 4. So this one is not there, it is in the secondary memory. So now what happens, this is the idea. So need for page replacement. If I somehow need now to access, let's say, B, then I have to bring back here. Okay, either I can use the free frame, and if free frame is not there, so let's say H was not being used, so I will put it into the secondary memory, bring B back. So basic page replacement algorithm. Find the location of desired page on the disk. Okay, so find the location of whichever page. When page fault occurs, so I will find where it is located on the secondary memory. Then we need to find a free frame in the main memory. If there is a free frame, use it. Otherwise, if there is no free frame, use page replacement algorithm to select a victim frame, bring the desired frame into the free frame, and update the page with frame tables. So restart the process again. So we will look at this. This is a simple algorithm. Let's see here. So page replacement, we find if what happens, says we have a victim page, so swap out victim page into the secondary memory, bring the desired page into the free frame now here. Okay, so page replacement algorithm, we want lowest page fault. We don't want that always. We want that all of the pages should be in the main memory, and evaluate algorithm by running it on a particular string of memory references and compute the number of page faults. So lower the page faults, that is lower the number of pages that are not found, it's better. So let's see, the reference string is 1 2 3 4 1 2 5 1 2 3 4 5. Okay, this is the memory access pattern, okay, that we are getting. So let's first see what they do. So reference string is these are the page numbers that are accessed. We have only 3 frames or 3 pages can be in the memory. So let's try to see. Initially we have we have only 3 frames. Only 3 frames can be there, or 3 pages can be there in the main memory. So I bring 1, then bring 2, bring 3. So 3 page faults are there till now. Then what happens? Now I access page 4. So page 4 is not there in the main memory. There will be a page fault. Okay, so +1, and we will remove the FIFO. It's the first in will be removed, and we will be bringing 4 here. Okay, so this is done. Now what happens? Again I want again 1 is not there. Okay, so what I do, page fault occurs, replace with the oldest one, which is 2. I bring 1 3 4 1 are there now. Then what I do, then again now 2 is accessed, 2 is also not there, so a page fault occurs. So 3, which was the first one here, now the oldest one is brought out, and 2 is brought in. So 4 1 2 is there now. We need to access 5. Again 5 is not there in the main memory, so we push out the oldest one, bring 5. So 1 2 5 is there. Now we see again we require page 1 is there, so it's fine. Then we require page 2, it's in the main memory, so it is fine. Then we require page 3, so page 3 is not there, so we remove 1, the first one there in the queue, and then put 3. Now what happens, 3 is there, so 3 is done. We require 4, move the last one out, so 5, 3 and 4 are there, and then finally we need 5, which is already there. So the number of times there was page fault, if you count those, so that will be initially 3, then 1, 2, 3, 4, 5 and 6. So there were 9 page faults. Okay, so total 9 page faults were there. Now let's try to see what happens if we have 4 frames in the main memory. So you will think that okay, there will be less page fault, but unfortunately this is a Belady's anomaly. Okay, so that's some person gave that anomaly and 4 frames. So let's see, 1, 2, 3 and 4. So this is done. So 4 page faults already we got. Then I try out 1. So 1 is there, good enough. So 1 is there in the main memory, no page fault. 2 is there, no page fault. 5 is not there, so page fault occurs. I bring back 5, put out 1. So 5 is done, then 1. So 1 is not there, again move out 2, 1 is there. And this is done. So now 2 is not there, I put 2, bring back 3 out. Okay, 4, 5, 1, 2 are there, then I access 3 is not there, I just removed it. So I need to remove 4, access 3 is done. Then they ask again for 4. This is really some unfortunate access pattern. So 4 is not there, you require 4. So bring it into the memory, remove 5 and then you require 5. So 5 you push here and remove 1. So now you see 4 were page fault initially, 1, 2, 3, 4, 5, 6. 4 plus 6, there was 10 page fault were there. Okay, so this is even more than 3. So you thought that okay, if I increase the number of pages in the main memory, there will be less page fault. But if you see here, so there were more page faults. Okay, so that is Belady's anomaly. So FIFO page replacement, that's what again they are trying to see. So we have page frames are there, and then they are showing us that how it was. So when there was 7 was pushed into the page table in the FIFO, 70 was there, 701, then 2 is pushed. So now what happens, 7 was the oldest one, so it was removed, 2 was put here. Now this 0 is the oldest, we require access of 0, this is fine. Then we require 3. So 3 when you require, it is not there, so 0 was the oldest. Now I replace it with 3. 1 is the oldest now. So now when we require 0, it's not there, so 1 is replaced here with 0. This is fine. Now which is your oldest, so you just need to keep track of that. 2 was the oldest and so on. So this is FIFO page replacement. And there we saw that okay, Belady's anomaly. So while we increase the number of frames, there was some increase in number of page faults also. Now let's try to think about some optimal algorithm. Okay, so optimal algorithm says replace page that will not be used for the longest period of the time. That's best. Okay, so replace the page. So this is kind of an offline algorithm, but it will be the best. I already know the input. Okay, what is the sequence of access of the pages, and then I'm deciding which one I should bring in the main memory. So replace page that will not be used for longest period of time. Okay, so 4 frames are there in the main memory. So I have 1, 2, 3 and 4. Then what happens, 4 page faults are there. Now what happens, 1 I access, 1 is there, then I access 2 is there. So now there are 5 I access. Okay, so 1, 2 are used, 5 I access. So what happens, let's try to see here. So 5 is not there, so I have to do some replacement algorithm. So which one should I replace with? So replace page that will not be used for longest period of time. So 1, 2, 3 and 4. So which one will be not used for longest period of time? So 1 is going to be used 2, 3 and 4. So 4 is not going to be used for the longest period of time, for 4 page time. So I will remove 4, bring 5 here. Then it is done. Then I require 1. Okay, so 1 is there. I require 2, 2 is there. I require 3, it is there. So then what happened? 4, it's not there. So again, so which one should I remove? So remove it with something that was will not be used for the longest period of the time. So only 5 is there. I can remove any one of them. Let's say I remove 1, and okay, so only how many page faults? 6 page faults. So how do you know this? Used for measuring how well your algorithm performs. So you cannot know this pattern sequence because it's online. How your code is accessing pages, you will never know. So this is just an offline algorithm which will give you the best page fault, minimum number of page fault, but you can never use it because this is assuming that okay, we already have the sequence. So optimal page replacement they are doing on some string, so which is I have 3 frames. Okay, and now let's try to see 701. So this is fine till here. Then I need to 701, 2 is not there. So which one should I replace among 701? So 7 is far away, very far away. 0 is very nearby, 1 is also nearby. 7 is the farthest. It is not going to be used for longest period of the time. So I will replace this. This is the victim page. 2 is replaced here. So now I need a 0. 0 is already there. It is fine. 3 is not there. Okay, now I need to find a victim page. So 2, I'm going to use it. 0, very nearby. 1. So 1 is very far. So I will replace with 1. So you see 3 is replaced here with 1. 203. So 3 is there now. 0 I require. 0 is here. 4. Again there will be a replacement algorithm. So 4, where should I replace it? This is the one. So 2 I just require it. 0 is there. 3 is there. So 0 is the farthest. I will replace 0 with 4. 2, 4, 3. So now 2 is used here. 3 is used. 0 is not there. Okay, again. So now there will be a page fault here for 0 is not there. So now let's see which one to replace with. 2 is getting used here. 3 is getting used even earlier, and 4 is not going to be used at all. So I will remove 4 and bring 0 here. Okay, so like this it will go on. So this is the concept that okay, optimal algorithm replace page that will not going to be used for the longest time, and if it is not going to be used, it's better to replace it with something that is going to be used now, and never replace something that is to be going to be used in the very near future. So this is the optimal algorithm, but it's not possible to devise one such algorithm. So we will see about an approximation of this, which is known as least recently used page. Okay, so that's all for this lecture. Next lecture we will learn about LRU algorithm. Thanks a lot.